Okay, everybody. So as promised, here is the rest of the notes for section 1.5. Shouldn't be very long, but again, use the remaining time in class today to work on your homework. Or again, you can pick up the practice test. I'm going to put it right on the front table there if you'd like to pick it up early. All right, here we go. So we just got done talking about natural logs, ln of x. And so now what we're going to do is graph them a little bit. So I'm going to sketch the graph of the function y is equal to ln of x minus 2 minus 1. So I guess the first thing I need to do is figure out what type of transformations I have on my parent ln of x. Now remember that if I'm thinking about my parent ln of x, ln of x, um, it's just basically got a vertical asymptote and then here, right? And we know that this x-intercept is 1 comma 0. And why did we know that? Because e to the x, it goes through 0 comma 1. We also know why e is so important is because the slope of the line as it passes through, the slope of the line as it passes through is 1. So in this case, it's still going to be 1. But so I don't know if I drew that exactly correctly, but that's why e to the x was so important. That's why log base e of x is so important. All right, so what we're going to do is take a look at these two transformations here. I see this one, and then I see this one. So this one is so remember inside, that's a right 2, and then this is a down 1. Okay, so all I'm going to do is take each piece and move it right 2, down 1. So right 1, 2, down 1. So this point right here, let me put it in red. This point right here is going to shift right 2, down 1, right? And then it's going to, think about the asymptote was at my vertical axis, that y-axis, so x equals 0. If I shift it to the right 2 units, that's going to put my asymptote right 2 units as well. So right there. So now this is just going to dive downward here. I'm not changing the pitch of the line at all. And then you're going to, connect in there. Ooh, yikes. Shouldn't be this little kink in there. A little hitch in the giddy up. But there's my new function, right 2, down 1. Okay. Okay. So now let's talk about, I guess I could have done that problem yesterday. Yeah, whatever. You get the idea. Inverse trigonometric functions. So one of the big things about inverses is using inverse trigonometric functions. Now remember that this is when I'm going to give you the coordinate and you have to work backward to find me the angle at which that coordinate exists. When we try to find the inverse of trig functions, we have a slight difficulty. Because the trigonometric functions are not one-to-one, they don't technically have inverse functions. Look, sine x is not one-to-one because it hits here and it hits here, right? That means the inverse of sine is technically not a function. Now, how do we change it so that this difficulty is no longer an issue? The difficulty is overcome by restricting the domain of the functions so that they become one-to-one. So now that's when we have to use the restricted domain. Okay. Now, what is the restricted domain on sine? Remember, the restriction on sine is negative pi over 2 to pi over 2. That way you get all values in there. Now, it's not a full rotation. Notice that it is not a full rotation. It's not a full rotation because if I went a full rotation, it would give me two places where it gets the same y value, right? So that means I only go from negative pi over 2 to pi over 2. Look, the graph is over here. And now this passes the horizontal line test. So we can see that, yes, it is indeed now one-to-one. The inverse function of this restricted sine function exists and is denoted by inverse sine or arc sine. Now, I'm going to have to take a little bit of an issue with this. We learned it in Algebra 2 as capital S sine, right? That's what we learned it as. The restricted domain had a capital. This is just another way to write it as arc sine. It is called the inverse sine function or arc sine function. And we can have the arc cosine or the arc tangent functions. We just have to be very careful about the restrictions on theirs. Now, I guess I should go over them. It looks like I don't even have them in here. No. Remember the restriction on, let me go here. The restriction on cosine is the 0 to pi. How do we write it? 0. Okay, yeah. X. is less than or equal to pi, and the restriction on tangent is the same as pi, or excuse me, the same as sine, negative pi over 2 to pi over 2. Okay. Thinking about it, why is that the case? Well, because think about cosine. It starts up at the axis here, and it goes right. So what we can say is, well, going from 0 to pi gives you the full range, right? It gives you the full option without ever overlapping twice. If you think about tangent, as soon as I get past that asymptote, well, that's a really good graph there. As soon as I get past that asymptote, it's going to happen again. So I just want one of these little pieces here, which is negative pi over 2 to pi over 2. Wow, that's a really Bush League graph there. Okay. Since the definition of an inverse function, we learned about this yesterday. Let's just jump straight into it. Okay, so the first thing we're going to do is evaluate inverse sine of 1/2. And now, again, they're assuming this. Right? They're assuming capital S sine. Okay. I think I'm going to look in my notes just to make sure that that's what they mean. Yeah. So they're saying capital S sine. So what I have to do is look at the unit circle and say, okay, what angle, because the output is the angle. The input used to be an angle sine of 60 degrees or sine. So if I change it to the inverse now, the output is the angle, the input is the actual the location. So now if I'm thinking about the sine being 1/2, that is really just one location right here. Thinking about it in terms of radians, that's that pi over 6 family, right? So that's my answer, pi over 6. Okay. And again, what you're looking at here is, because I know the y value, this is because I'm looking at the sine, I know that I'm looking for the y value that is 1/2, right? What angle has the y value of 1/2? Pi over 6. You may be thinking to yourself, wait, there's another option. There's another option over here, right? But remember, the restrictions on the domain are only giving us this first and fourth quadrants. That's the only thing that I care about on the restricted domain. How do I know it's a restricted domain? We should have capitalized this. That's why I wrote it right there. But I can tell by arc sine over here. Now, this one's a little bit interesting because, think about 1/3. I don't know about you guys, but I've never seen a 1/3 on my unit circle. So what the heck is going on there? Well, here, think about it this way. Arc sine of 1/3 basically says if you've got an angle theta, I guess I should have made that a little bit bigger, but if you've got an angle theta, the angle is equivalent to having the sine of 1/3, opposite 1 over hypotenuse 3, right? Opposite 1 over hypotenuse 3. So really, I want to find tangent of that theta, right? Theta, this angle is going to have the sine at 1/3. Sine of theta is equal to 1/3. So that means opposite 1, hypotenuse 3. So really, I just want to find tangent of that theta. Tangent is opposite over adjacent. So let's just solve for this piece in here. X squared plus 1 squared is equal to 3 squared. So x squared plus 1 is 9. X squared is 8. And then when I square root it, just reducing it down, the square root of 8 is 2 radical 2. So we've got 2 radical 2 sitting down here. So tangent is opposite over adjacent, 1 over 2 radical 2. And just to rationalize, bringing this radical 2 up to the top, 1 over, radical 2 over 4, right? Because I multiply by radical 2 over radical 2. So that will give me radical 2 on top, and then 2 times, those go together to make a 4. Radical 2 over 4 is my tangent theta here. Okay. All right, last problem here. Simplify the expression cosine of inverse tangent of x. Cosine of inverse tangent of x. I'm kind of going to do the same thing. I know x, tangent, whoa, yikes, what am I doing? Tangent of some theta is equal to x, right? So that means I'm going to draw this triangle where tangent, yikes, tangent of theta is equal to x. So let's put theta here. The opposite of tangent is equal to, or sorry, excuse me, the tangent of x is equal to opposite over adjacent. So opposite over adjacent. And then I can evaluate this hypotenuse because look, inverse tangent of x is really theta. So that means all I really want to find is cosine theta, right? So cosine theta is adjacent over hypotenuse. I just got to figure out what my hypotenuse is. Let's call it h. H squared is equal to 1 squared plus x squared. So h is equal to 1 plus x squared. Oops, sorry, h squared. So h is equal to the square root of 1 plus x squared. They wrote it as x squared plus 1, but same thing. So this is the square root of 1 plus x squared. So when I go to evaluate the cosine, the adjacent is 1. The hypotenuse is the square root of 1 plus x squared. Now, I would be okay if you had that as an answer. The book rationalizes, again, I think I talked about this in class, rationalizing is going to kind of fall by the wayside. But if you wanted to rationalize, it would look like this because there's just a 1 on top. It's another valid answer there. All right, that's all the notes for today. Hopefully we're having a good day and you can have the rest of the time to work on your homework. Go ahead and pick up that practice test if you would like it as well. See you, everybody.